Welcome to bonding in homonuclear diatomic molecules. So homonuclear, remember, homo means same, nuclear means nucleus. So homonuclear means we have the same nucleus, so the same element type. It's diatomic, which means we have two atoms. So we have two atoms of the same element. And so let's look at something like dilithium, lithium-2 molecule. So each lithium atom has an electron configuration of 1s2, 2s1 before bonding. Only the valence electrons are involved in bonding, so we're not concerned with those 1s electrons. We're going to ignore them. So we're only concerned with the 2s electrons. So if we look here, we have one 2s electron from this lithium, one 2s electron from this lithium. When we put them together into our sigma 2s orbitals, we get two of them down here. We don't have any left over to go into our sigma 2s star, our anti-bonding orbital, which means that now our bond order is 2 minus 0 over 2, which is 1. So we expect dilithium to be a stable diatomic molecule. It is, in fact, a stable diatomic molecule compared to separated lithium atoms. But at room temperature, lithium doesn't actually exist as diatomic molecules because of the metallic bonding. Metallic bonding is actually stronger than this covalent bonding would be. And so it's more energetically favorable to have many metallic bonds between many lithium atoms and to form these diatomic molecules. So we actually see lithium existing as a metal, in the solid state, and not as diatomic molecules. But diatomic molecules are still more energetically favorable than separated lithium atoms would be. So now let's look at the beryllium diatomic molecule. So each beryllium atom has an electron configuration of 1s2, 2s2 before bonding. So now we have two electrons in there in the 2s. When we, again, we're only interested in the valence electrons, so we're ignoring the 1s. So when we combine together our 2s, when we put them in, two of the electrons move down, two of the electrons move up. The bond order then is 2 bonding electrons minus 2 anti-bonding electrons divided by 2, which is 0. So diberyllium is not stable compared to the separated beryllium atoms. There's no reason for them to bond together, so it essentially doesn't happen. There's nothing pushing them apart either, but there's nothing holding them together. So if they collide, they'll just move apart again. Now let's look at diboron molecule, B2. So each boron atom has an electron configuration of 1s2, 2s2, 2p1. Before bonding, again, only valence electrons are involved, so we're going to ignore the 1s2. We're only concerned with the 2s and 2p electrons. So remember that in each boron atom, there are 3 2p orbitals that are all mutually perpendicular to each other, looking something like this. So 2 of the sets of 2p orbitals are parallel and can form pi bonds, while one set can directly overlap to form a sigma bond. So let's first look at the combination of the directly overlapping p orbitals, so this guy and that guy. So the bonding orbital is formed by the overlap of the identically signed lobes, so like this. So constructive interference causes the bonding orbital to look something like this. Causes an increase in electron density between the two nuclei in that overlapping region. So this now, we get more electron density in between the two. That will be a bonding orbital because that will tend to pull our our nuclei together. If we have oppositely signed overlapping orbitals, then we get an antibonding orbital, so that tends to push our electrons to the outside of our nuclei. That will tend to pull our nuclei farther apart. This is because of destructive interference in the overlapping of those two orbitals. So now let's look at the combination of the parallel p orbitals to form the pi bonds. So we see similar constructive and destructive interference in the bonding and anti-bonding orbitals. And so if we have the constructive interference, we get something like this, a bonding orbital. So again, we have our nuclei exist in here, not there. We have our nuclei existing in there. So again, these are pi orbitals. They're not directly on the line in between the two nuclei. They're above and below, or in front and behind of. But this is a bonding orbital because this nucleus will tend to be pulled this direction. That nucleus will tend to be pulled this direction. So they're going to tend to be pulled towards each other. On the other hand, if we have oppositely signed lobes. When we add those together, now we have a node in between, and now a nucleus that's here and a nucleus that's there will tend to be pulled apart. So this will be an antibonding orbital, that will be a bonding orbital, both pi molecular orbitals. So the expected, note this, expected energy diagram of the molecular orbitals for diboron is shown over here. So we expect the two 2s orbitals to combine to form a sigma 2s and a sigma 2s star. They'll both be occupied with 2 electrons. Then we'll have 2 electrons left, one from this atom in the 2p and one from this atom in the 2p. We'll combine those together. We'll get two pi 2p orbitals here. We'll get 2 pi 2p star orbitals up there. We'll get a sigma 2p orbital that will be occupied by 2 electrons. We'll get a sigma 2p star orbital that is not occupied by electrons up there. And so the bond order then becomes 4 bonding electrons, because we have this one and that orbital that are both filled with 2 electrons apiece. So we have 4 bonding orbitals, 4 bonding electrons rather, minus these 2 antibonding electrons. So we have a bond order of 4 minus 2 divided by 2, which is 1. So the diboron molecule should be stable compared to the separated boron atoms. We expect to see 1 bond being shared between those two atoms. So most substances exhibit no magnetism until they are placed into a magnetic field. But substances that are attracted towards a magnetic field experience paramagnetism, and we call them paramagnetic. This is something like iron. If we take iron and we put more iron next to it, there's no attraction there. But if I take something that is a permanent magnet that has a magnetic field around it already, and I put iron nearby, now the iron gets attracted. So the iron is paramagnetic. But something like plastic, let's say, is not paramagnetic. Substances that are repelled from a magnetic field are called, or experience diamagnetism, and they're called diamagnetic. And so it turns out that paramagnetism is caused by unpaired electrons, and diamagnetism is caused by paired electrons. Now, paramagnetism is significantly stronger than diamagnetism is, and so something like plastic, it is repelled by a magnet, but it's not repelled very strongly. It's significantly weaker than the attraction force experienced by something like iron would be. So in normal daily life, we don't really notice that repulsion very much, but we do notice that attraction force. So iron exhibits paramagnetism because, as I said, iron, we see here, now I'm leaving off the core electrons, but here we see iron has an electron configuration that ends in 4s2, 3d6, which means we have 4 electrons here that are unpaired. So iron atoms should exist paramagnetism because unpaired electrons exhibit paramagnetism or cause paramagnetism. Whereas something like calcium up here, which has an electron configuration of 4s2 with no electrons in the 3d, so there are no unpaired electrons because the only electrons that are there are paired. Calcium would exhibit diamagnetism. Okay. So, do you think copper would exhibit para or diamagnetism? And if it experiences paramagnetism, do you think it's stronger or weaker than for iron? Pause the video and think about it. It turns out that copper would experience paramagnetism because we do have this 1 unpaired electron here. These are all paired. But we have 1 unpaired electron there compared to 4 here, so approximately, we'll get approximately 1/4 of the attraction for copper that we would for iron. Now that's assuming that it's not bound to anything. So. Alright, so do we expect our diboron molecule to be paramagnetic, or do we expect it to be diamagnetic? Let's see. In our molecule, we have some paired electrons. We have some more paired electrons. We have some more paired electrons. And we have no unpaired electrons. So we expect our diboron molecule to be diamagnetic because we have no unpaired electrons. But it's actually paramagnetic, which means something's wrong with our diagram. This means that our model is incorrect because it can't adequately explain why diboron is paramagnetic. And it turns out that the 2s and 2p orbitals can mix somewhat, which causes our molecular orbitals to have slightly different energies than we expected them to. And so we instead have some molecular orbitals that look something like this. So note now that we've swapped the positions of the sigma 2p and the pi 2p orbitals. The pi 2p orbitals are lower in energy and the sigma 2p orbital is higher in energy. And this now means that now because we fill in the lowest energy orbitals first, we fill in our pi orbitals before we filled in our sigma orbital. And that means that now we have some unpaired electrons in there. That now causes our paramagnetism to be seen. Note that in this case, the bond order is still 1 because we have 4 bonding electrons and 2 anti-bonding electrons. So 4 minus 2 divided by 2 is still 1, right? So the bond order is still the same. We haven't changed the number of bonds. All we've changed is whether it's paramagnetic or diamagnetic by changing this order here. So if we look at some of the paramagnetic and diamagnetic properties of the other diatomic molecules, we can see that here. So we see with boron, carbon, and nitrogen the same swapping of the sigma and pi 2p orbitals, where the pi 2p orbitals are lower in energy than the sigma 2p is. With oxygen and fluorine, we don't. So what that means is that the diboron is paramagnetic, dicarbon would be diamagnetic, the dinitrogen would be diamagnetic. But when we get to oxygen, oxygen would be paramagnetic. Yes, oxygen gas is in fact paramagnetic. It does in fact respond to a magnetic field. Now, we can't see it with oxygen gas for 2 reasons. One, because it's colorless. We don't see oxygen gas in the atmosphere. But also because it's way too, it's not anywhere near dense enough for us to see a cluster of oxygen unless it's in liquid phase. But if we get liquid oxygen, which is really cold, and we put it in the poles of a very strong magnet, we can see that it will hang suspended there. So, fluorine would be diamagnetic because those electrons are all paired. So that was bonding in homonuclear diatomic molecules.